Hello everyone. In this video I'm going to simulate an atmospheric boundary layer flow using OpenFOAM. So this is my first case in OpenFOAM and I have used this case as a way to learn the workflow in OpenFOAM, and also I feel that the way we do things in OpenFOAM really helps you to understand the in and out of the CFD behind. So I hope this video helps anyone who is new to OpenFOAM and who is eager to get started with OpenFOAM. So before we start with the simulation, let me briefly explain the case. So I'm going to reproduce the CFD simulation case discussed in this article. So they have basically validated an atmospheric boundary layer flow over a single building which is at model scale using wind tunnel measurements. So for comparison, they have monitored the coefficient of pressure values across different phases of the building in CFD with the coefficient of pressure values from the wind tunnel. So for my case, I will be reproducing this CFD simulation and try to get the coefficient of pressure contour plot over the windward face of the building to be matching with the result given here. Also, to speak a little about the theoretical aspects of atmospheric boundary layer. So when it comes to problems where you want to model pollution, dispersion and deposition by wind or urban city scale flows, or even flows with wind turbines, there you have to basically work with atmospheric boundary layer. So in our specific simulation, we are dealing with a neutrally stratified, fully developed atmospheric boundary layer, and that's characterized by three main features. So you have horizontal homogeneity, which means you don't have streamwise gradients, and also it is neutrally stratified, and the sources of turbulence is basically because of shear and because of the ground roughness. So you have this equilibrium between mean flow and turbulence, and so the turbulence kind of is sustained and remains stable. And the other thing is where you have dissipation, there is local equilibrium between production and dissipation. Okay, so these are the three main characters of this neutrally stratified atmospheric boundary layer. And within CFD, to model this type of flow, we basically use wall functions, and these are log-low wall functions, and in order for them to be valid, the cell size or the Y plus range should be in the log layer range between 30 to 300. So that's one requirement that we have to meet with the mesh in our simulation. And also if you notice, the key parameter within these wall functions is the aerodynamic roughness length. So that's the parameter which models the surface roughness. So between terrains like an urban landscape or between an agricultural terrain, this aerodynamic roughness length will vary, and by tweaking that we can actually tweak the atmospheric boundary layer profiles. So the key takeaway is that we will be using these wall functions within our CFD simulation to basically model the inlet profiles and also to model the different boundary conditions, especially on the ground. Okay, so finally let's take a brief look at how things are done, or how to use OpenFOAM in a very basic way. So once you have done the installation, and if you go to the installation folder, you can find tutorials to begin with. So usually every beginner start by copy pasting a case folder from the tutorials and then editing the files in it. So it will be clear when I explain further. So within this tutorials folder, you have different types of simulations. Then you go to the basic, you find symbol form, incompressible flow case. Then you have an example. This here is a case folder, and within the case folder, or every case folder, you basically have 3 subfolders before you run the simulation, and inside each of these subfolders you have text files. So for example, inside the 0 folder you have text files relating to the boundary conditions for velocity, pressure, turbulence, and so on. And within constant you basically store your geometry file. In our case we have a STL file for the building, so that will be stored inside a subfolder within the constant subfolder, which is named tri-surface folder. And in case of the systems folder, you basically have text files relating to mesh settings, solver settings, and so on. And eventually when you run the simulation, a post-processing folder will appear, and so that's how it works. So in contrast to clicking on buttons and selecting different models, we will be going hands-on in case of OpenFOAM. So in order to choose between parameters and select between models, we have to edit these text files and set up the simulation. I think that's really good to learn things in a better way, to understand how you set up the simulation and all the models and how each parameter influence the simulation and so on. I think that's enough prerequisite knowledge for to get started with. So from now on we will be following the routine workflow. We will cover the geometry, then we will set up the domain and the mesh, then we will set up the physics, then the solver, then we will run the simulation and do the post-processing. So let's jump into geometry. So the computational domain is defined according to the best practice guidelines for urban flows in literature. So according to that, the domain dimensions are parameterized with the building height. For example, the upstream domain length is 5 times the building height, and it is 2.5 meters in our case. Similarly, you have different dimensional requirements in downstream and lateral directions. Okay, so I have followed this and basically estimated what should be the overall domain dimensions. So I have used 5H in the upstream, 12H in downstream, and 5H in both lateral and vertical directions. So according to that, you have 9 meters in x-axis, 3 meters in the y-axis, and 6 meters in z-axis. Okay, so now we have to create an STL mesh file for the building, and I'm using FreeCAD for that. And also I have created a ground object to visualize the scale of the domain. So for using an OpenFOAM, we only require the building block, and I have positioned the base of the building at the y=0 or the ground plane, so we don't really need the ground object. So to export this file, just click on the solid body, go to file, export, and save it as an STL mesh file. So I have already done that, saved it some folder, and later we will be copy pasting this to the case folder. So maybe I can also show you where it is placed in the case folder. So go to Ubuntu home, so just navigate to the case folder, and inside the constant subfolder, if you have a tri-surface folder, then paste it inside here, or else just create one and name it as tri-surface, then you paste the building STL file here. So later we will be accessing or calling this file in one of our mesh settings text file. Okay, open a Linux terminal, navigate to your case folder, and sorry, in my case, and if you do an ls, you can see the subfolders, and the mesh settings files will be within the system subfolder. So navigate to there, then if you do an ls, you can find block mesh dict and snappy hex mesh dict. So the overall computational domain is edited in this block mesh dict text file. To edit that, type in nano block. Okay, so this is the text file, And in here initially we define the vertices for the domain. So these are according to the domain dimensions that we estimated earlier, -3 in the negative x direction and 6 meters in the downstream, and so on. Then we have to define the hex block using these nodes, and this 0, 1, 2, 3 are the indices of the respective nodes here, and just follow this convention. And next to the hex block you have the number of cells in each direction, and you have a required grading in each direction. So I'll explain how I ended up with these values for grading and number of cells, but this is where you set it. And apart from that, you have to specify the boundaries and boundary types in this text file. So you have different types of boundaries available in OpenFOAM. So you can read about it. So these are the types, and you have patch, which is a generic type of boundary where you have to define how the boundary conditions for pressure and velocity and everything. So I'm following that in the case of both the inlet and the outlet. And the ground is a wall type boundary, and the top and side faces are all symmetry planes. Okay, and a similar convention is used also in the article. And one more thing to keep in mind is that in OpenFOAM we follow a right hand rule for numbering the indices for each face. So whichever face you choose, the normal to the plane should point outward, and accordingly the numbering of the nodes should be done in the anti-clockwise sense. Okay, so that's how 0473 but not 0374. Okay, so that's how it's done. So the next I can explain how I estimated the number of cells and the grading that we require. So I have done some hand calculations for that. So from the article you need couple of information. So first of all, we want to know the aerodynamic roughness length for the ground, which is given here as 0.0018, and also we need a reference velocity from the flow field, which is 7.1 meter per second, measured at the building height of 0.5 meters. And using this information we can basically estimate the friction velocity, and using the friction velocity we can calculate the first cell height for a target y plus. So I am aiming for a y plus of value 50, and according to that I have calculated the first cell height, which is dy1 in my case, and that's around 2.8 millimeters. So in the article they have mentioned the final first cell height close to the ground, and that's 2.5 mm. So my estimated first cell height is close to that, so that's totally fine. And the next thing is to estimate the number of cells that we require to be defined in the text file. So for that I need one more parameter, which is to set the per cell expansion ratio. So this is the usual growth rate that we find in the mesh settings in commercial tools. So this is basically defined as the how much bigger is an adjacent cell compared to the previous cell. So for example, like if we consider the first and second cell, then how big is second cell compared to the first cell? So that's per cell expansion ratio. And the grading in OpenFOAM is defined as the ratio between final cell height to the initial cell height. Okay, and the per cell expansion ratio, using that we can define the final cell height as a geometric progression value, initial value times the growth rate to the power of number of cells -1. So coupling these two equations, we can find the grading as first cell expansion ratio to the power ny -1, and that's actually calculated as 88.19. So the objective is that using the target y plus and the target per cell expansion ratio, we basically calculate the grading and also the number of cells required in y-axis. Okay, and I have also done one more thing to make the number of cells proportional in x and z axis. I have basically estimated a base cell count in each axis. Then I have found an factor of multiplication which is based on the minimum of the dimensions of the building, which is 0.25 meters. So here if you substitute or expand this, fx would end up as 1 and fy is bh over minimum of the dimensions, which is 0.5 by 0.25, which is 2. So the objective is to basically make everything a factor of the smallest building dimension. So if you have too many buildings, then consider the smallest building then as a reference. And according to that, we estimate a basic cell count. And once you evaluate the capital Ny required for the grading and the y plus requirement, then you basically can estimate a factor j, something like ny by the basic cell count in y-axis. Then that would be 48 over 12, which is 4. So then you multiply those with the basic cell count in x-axis and you eventually end up with this value. So I find this as a systematic way to estimate the number of cells rather than just going with trial and error and things. Okay, so I have used this. Then I will be specifying this here. Okay, so based on the y plus, you can tweak around the grading and make use of hand calculations for that. Okay, so this is the first and primary text file that we need to edit. Then once you have done all the changes, to save it, press Ctrl O. Then to confirm the file name, press enter, and then to exit the text file, press Ctrl X. Okay, now you can actually create the computational domain and the background mesh by typing in block mesh. Yeah, so now we have created the background mesh. Now we want to visualize it. For that, maybe you can create a form file within the case folder. So to write a form file, type in touch montessori.form. Okay, so then we can open this form file in ParaView and see the mesh. Okay, so I have created the form file, and if you do an ls in the case folder, you can see that a new file has appeared. Now let's go to ParaView and open this. In ParaView, go to files, open Montessori, and this is the file that we have created just now. Click OK, apply. Okay, so this is the computational domain, and to see the mesh and the grading, you can see thin cells near the ground to match the y plus. Then you have grading which makes the cells bigger and bigger as we go up in the y axis. And since we followed the uniform grading in, you have almost uniform cell size in the x and z direction. Okay, so this is the background mesh. So the next step is to modify this mesh near the ground and body fit the building object into it. Okay, so let's insert the building into the mesh. For that, we have to edit the snappy hex mesh dict file system folder. You can type in nano dict. Okay, so this is where you insert the STL file. Here you can find the STL file that we created, and basically we are controlling two operations through this text file. So first is something called cancellation. Then you have snapping. So castellated mesh, when it is enabled, basically cuts the background mesh that we created in block mesh dict. And for cutting the mesh, we use the surface from the STL file. And once we have cut the mesh, we will have some incomplete cells at the cut. Then probably we have to move the nodes near the cut to match with the surface of the STL. And that operation is basically snapping. And that's an iterative process. So basically here we have to specify the STL name, and then within the geometry block you also specify the refinement regions, volume refinement regions that you want to add. So in my case I'm using a wake refinement, also starting slightly upstream the building. So I have defined this region beforehand within the geometry part. Then have the default castellated mesh controls. I haven't modified much here. Then you have surface refinement for the building. So here you can see the refinement levels. The left value is the minimum value and the right one is the maximum value. So you can set it as 3 or 4 or 1 or 2 or something like that. But I don't want to complicate things at this point, so I'm using a uniform cell size across the surface of the building, so with refinement level 3. Okay, so you basically cut the cells 3 times. So that's surface refinement mentioned here. Then you have regional volume refinements, and here the box wake is the region that we defined in the geometry part. Okay, here it's named box wake. So we call it here and specify the level of refinement, which is 1. So the base cells will be cut once. Then you have something called a features block. So when you want to retain the sharp edges in the object, we usually have enabled the features block. But you need to have a supporting file, text file for this. I can show it to you in a bit. Then you have to mention this location in mesh value. So this is basically some random point within the fluid domain. So OpenFOAM after snapping or after cancellation, it doesn't know which is the solid part, which is the fluid part. So we have to mention it ourselves to mark the outer region of the snapping as the fluid part. So you can pick some random point within the fluid domain, then mention it here. Yeah, and resolve feature angle is kept 30 as a default thing. I haven't changed that. Then you have snap controls. So depending on the type of geometry you have, you can modify the values here and see how the mesh, body fitted mesh changes. So since I have a sharp cornered object, I don't want to smoothen the corners. So if you have a smooth object or a circular or cylindrical building, something like that, then depending on the value you can see that the object is faceted or smooth. If you have a higher value of a number of smooth patch, then you possibly have the surface resolved the maximum. Okay, then you have the tolerance, which specify how aggressive the snapping can be. Then you have like I said, the snapping procedure, the mesh adjustment is an iterative process. So based on having the number of iterations, the convergence will be depending on it, and also inversely proportional to the meshing speed. Then you have some damping factor for this iterative process, which is by default I set it as 3. Then you have mesh quality controls. I have kept the default values. I haven't changed there. Then you might have noticed that in the beginning I haven't enabled add layers option, which is basically to have inflation layers. So I have disabled it here, and instead I'm using grading. But you need to keep this as a default in the file, but we won't be using the inflation layers. So the key things, we have to insert the STL file. We have to specify the refinement zones here and the refinement levels here. And also this number of cells between levels is basically to specify how smooth the transition between levels are. And for the refinements, volume refinement and surface refinement, you have different options. You can have levels based refinement, where the refinement happens as spherical fronts around the object of interest. I think that's more suitable for objects which has round surfaces. In case of cornered objects like the building that we have, it's better to have box refinements surrounding it. So that's one thing that I decided to choose within this file. Then once you have modified everything, just save it, Ctrl O, overwrite, enter, and then Ctrl X. So now you have the refinements and snapping control, everything set. So go back to the case folder, and to execute the snapping operation, type in snappy hex mesh overwrite. So it will start the meshing and the refinements. Okay, so it took almost 3 minutes to complete the meshing, and the final snapped mesh has almost 1.2 million cells in it. And after the meshing is done, you can check the mesh quality by typing in check mesh. And if it turns out everything is okay, you will get a confirmation, and it's good to proceed to setting up the physics. Okay, so these are the mesh quality index, and you have a final okay for the mesh. So the maximum aspect ratio is 24. It will be at the top portion of the mesh where the grading is maximum. Then you have the max skewness, which is 0.35, which is really good, and you have a mesh orthogonality average is 3.5. That's okay. So overall the mesh is good. So now we can finally visualize that. So go back to ParaView. I have the form file already open. Just reload the file. Okay, so it's loaded. If you zoom in, you can see the building inside. Okay, with the body fitted mesh. So you have surface refinement level 3, and you have a region refinement, volume refinement surrounding the building and in the wake with refinement level 1, and everywhere else you have the base cell resolution. So this is our final mesh. So the next step is to set up the physics and the boundary conditions. Okay, so let's do that. To set the boundary conditions, we need to access the 0 folder present inside the case folder. So go to cd 0, change directory. Then if you do an ls here, you can see a text file for velocity, dissipation rate, turbulent kinetic energy, turbulent viscosity, and pressure. So these are text files where you have different boundary conditions for all the boundary types that we have defined. So first of all, let's set the velocity. So you can type in nano u to edit the text file. So within the velocity text file, first of all, we need to define the velocity condition at the inlet. So what we want to do is to have the log-low wall function set at the inlet, and for that we need to know the aerodynamic roughness length to be used. So in the article you have two aerodynamic roughness length mentioned. To generate the inlet profiles, they have used a aerodynamic roughness length of 0.008, while we earlier saw that the aerodynamic roughness length for ground is actually different from this, and that was 0.0018. So there is that distinction. So accordingly, I have chosen 0.008 as the aerodynamic roughness length, and have different boundary conditions available in OpenFOAM. And with atmospheric boundary layer flow modeling, you have certain wall functions already defined that we can use. So I'm using from this list of wall functions. So you have rough wall functions where you have turbulent viscosity in the name, and you have smooth wall functions without the turbulent viscosity in the name. So I'm using atmospheric boundary layer inlet velocity wall function, and you need to specify these parameters to completely define the wall function. And uref is 7.1 meter per second, measured at 0.5 meters height, and specify the flow direction and also the vertical direction. So here, even though it says set direction, so that's the naming that we saw in the wall function. However, the direction is actually along the y-axis, so that this is a unit normal along y-axis. And then you have this d, which is displacement length, that if we have a ground object in the domain, but we don't have one, so we don't have to do anything with that, so just keep it as 0. Then you specify a default value 7.1, but the values will be assigned according to the wall function, and if that doesn't apply to some region, then it will pick from this default value. So that's the same case as the internal field. You have a kind of an initial condition in the domain, so 10 meter per second. Okay, so that's the boundary definition at the inlet for velocity. Then you have at the outlet a zero gradient condition. At the wall you have no slip wall, and also at the building you have no slip condition. And apart from that, on the top and sides have symmetry plane condition. So this is the velocity text file. So now again save it, Control O and Control X. Okay, so now we want to edit the epsilon file. So open the epsilon text file. Then you have the inlet wall function, which is atmospheric boundary layer inlet epsilon. Here also we use the roughness length as 0.008, and at the outlet we use a zero gradient type condition, and in the ground we use atmospheric epsilon wall function with set 0 0.0018. So, and for building you have zero roughness length, so basically it's a smooth wall function, epsilon wall function, and all other faces have symmetry plane condition. So save it, Control O and Control X. Now let's do the turbulent kinetic energy, and for K at the inlet we are using atmospheric boundary layer inlet K, again set 0 set to be 0.008, and at the ground we are using a KQ wall function, which basically enforces a zero gradient condition at the ground, and also similarly at the building faces. And apart from that, again at top and side boundaries we are using the symmetry plane condition. Okay, so again save it, Control O and Control X. And finally we want to specify the turbulent viscosity condition, so nano nu T. This is where we specify the surface roughness to the ground. So here at the inlet it's basically calculated from all the wall functions that we have set. At the outlet we have a zero gradient condition, and at the ground I'm using a atmospheric newt K wall function, and you have to specify the roughness length for this. And at the building I'm using a newt K wall function with smooth wall function. So these are the boundary conditions, and one more thing is the pressure. So again save this file, Control O, enter and Control X. Now if we check the pressure file, you have outlet pressure set as 0, and everywhere else we are using zero gradient, and at the symmetry planes as symmetry plane. Okay, so again save, Control O and then Control X. So now we have all the boundary conditions defined. So next we can look into the solver settings. So for accessing the solver settings we need to go to the systems folder. So then if you do an ls here, so the control dict basically contains the solver settings, and the numerical schemes different schemes that we want to use to solve different equations will be present here, and the FE solution has basically all the under relaxation factors and everything inside. And this is something which I missed to explain. So we saw the features block within the snappy hex mesh dict. So this file is a supporting file for that feature to work. You have to create a form file like this and basically specify the included angle. So this works like the resolve feature angle. So when your geometry has sharp edges and when you want to retain those in the mesh, it's better to use this feature. So it might work without this feature, because then the snapping algorithm has to find the edges and do that. With this feature, that process will be easier. That's how I understand this. So I have added this file. So now we can look into control dict. For that, control dict. So here you can set the start from. So if you want to stop the simulation after a couple of iterations and modify some parameters like the under relaxation factor and continue the simulation from there, then you can modify here. Instead of start time, you can latest time, and it would start from where you stopped. So right now I'm using it as start time itself, and you can specify which time step to start from, and you can specify the end time. So what I usually do is keep the end time a small value, maybe 500 or 1000 iterations, and then I will be probing a velocity probably in a attached flow region like the upstream of the building. And once I have a stable value, a converged value in the upstream part, I will look for the residuals. How does that behave? Is it oscillating or not with respect to some equation? Then probably I will decide to modify the under relaxation factor at that point and then continue the simulation from there. So I usually follow that strategy. So then in that case, I keep end time as like 500 or 1000 and then continue from there. Then you have this write control. So after this, so in the later part of this file, we are setting up some functions and probes like the reports or monitors that we usually have in commercial tools. They are written at specific time intervals. So that's basically set here. The solution will be written at every 50 times. So otherwise you will have too many result folders and it will consume a lot of space. So you can basically control it here. Then so that's most often used parameters. Then in the functions, I'm basically calculating the y plus over the surfaces, and then also we want to post process by comparing the coefficient of pressure. So I have a function to calculate coefficient of pressure. You can basically add this. I have used it as an expression. So, and one more thing to note is that in OpenFOAM, the pressure output is actually pressure over density. So when you try to substitute it in the expression for CP, you can see that the density cancels out. So you basically have an expression like the OpenFOAM pressure minus the OpenFOAM reference pressure over 0.5 velocity, half rho v square. Yeah, not square root, square. So that's how it's done. So you don't have to worry about the missing density here. It's already accounted for and it's cancels out. So that's about CP and pressure. And also, like I said, I am probing a velocity field at 3 locations. For the first location is 0.9 meters in front of the windward face, and this is where the reference velocity of 7.1 meters was recorded from the wind tunnel measurements, and a similar location in the leeward side and at 1 meter or 0.5 meters above the top face. So I'll be probing these three values and monitoring convergence of the flow field with iterations using that. So it's always a good practice to have probes along with monitoring the residuals. Okay, so just check for templates, how to add functions, how to add probes, and then add it here in this text file. And also, so save it, Control O and Control X, and in the numerical schemes, type of numerical schemes used, so you can control the different upwind scheme or whatever numerical schemes that you want to modify. So right now I haven't changed anything, I'm following the default settings. Okay, Control O and Control X. And about the under relaxation factors, I often modify that in between the simulation depending on the nature of convergence. So that's edited in this file. So you have this, the pressure equation is solved using this GIMG solver, and you have a symbol solver for pressure velocity coupling, and you have the under relaxation factors mentioned here. So for the pressure right now it's 0.3, and for velocity it's 0.7. So I usually start with bigger values for or bigger jumps in the initial iterations, and once I have the flow stable and steady in the upstream part, then I usually, depending on the residuals, decrease the under relaxation factors to have convergence. So, and also have used a limiter for epsilon to avoid any unnecessary divergence. Okay, but maybe you can skip the limiter. I don't think it's really necessary in my case at the moment. So these are the text files that we want to take a look at. So then again Control O and Control X. So we have everything set up, and yeah, so and one more thing that we want to check is the turbulence model that we are gonna use. So for that we go to say the case folder, then that's present inside the constant folder. So 0, then ls, and you can see the turbulence properties. So nano turbulence properties, and here you can see the type of simulation, run simulation, and the turbulence is on, and the turbulence model is chosen as realizable K epsilon model. Okay, so the print coefficients is on, so you can see what are the coefficients used within the realizable K epsilon model. Okay, so you have some empirical coefficients involved. You can see that while you run the simulation. Control X. So we have basically set up everything. Now we want to run the simulation and see how it goes. Okay, so for that go back to the case folder, and to run the simulation you will be using typing in symbol form, which is incompressible flow solver. Okay, so if you type enter, the simulation starts to run. So these are the coefficients present inside the turbulence model. So it's starting to iterate. So these are the velocity residuals, and you have the pressure residual, continuity residual, turbulent kinetic energy, and epsilon residuals. Okay, so let's wait a bit and let's see. Also maybe I can show you the probes. So usually I open a separate terminal, then you can type in this command. So it basically if I open the case folder, go to, so you can here see a post-processing folder is appeared. So just open it, then you can see the velocity probes and y plus probes. So this is created because we have defined the settings in the control dict. Once you open it, it does have a u text file, velocity text file, which contains the three velocity vectors. So what we are going to print here is basically the final entry or the last line of this text file. Okay, so this command basically does that. And if I type in, okay, so again we have to navigate to the case folder. Before that, then we type it again, and you can see the probes. Okay, so by monitoring the convergence real time, we can actually see the progression of the solution. Okay, so I keep it beside the residual so I can see when to stop and when to, if I ever need to modify the under relaxation factors for some equation and so on. Okay, so you can see that the first vector is the probe in the upstream location, and this one is the probe in the downstream location. This one is the probe in the top location. So usually the upstream location converges faster, and it takes a bit to converge in the wake, the second probe, and also and relatively sooner will it converge in the top of the building. Okay, so now we have to wait till end of 500 iterations and see whether we need to modify something or not. So you can see that it's starting to converge, and it's very early to say that, but it will converge. And when you can see that the velocities no longer differ at each of these probes, then you have totally converged situation. Okay, so let's wait. So 500 iterations has passed, and you can see that the ground y plus is having an average of 72, while the building y plus is around 7. So that is okay for the simulation. So the important thing is to make sure that the ground y plus is in range. And when you check the residuals, you can see that the velocity is converging really well, and also the turbulence is converging properly. And the only thing that requires further convergence is the pressure residual, which is also going fine. So now we don't have to modify the under relaxation factors, but we want to continue running the simulation maybe till 1000. Okay, so let's edit that within the control dict text file. cd, then you basically modify here maybe 2000 iterations, and instead of start time, modify it to latest time. Okay, now save it, Control O and Control X. And also, if you monitor the velocity probes, you can see that the upstream flow is very well converged. You have convergence everywhere. So let's continue running. So type in, go back to the case folder, type in symbol form. Okay, so then it starts to solve again from the 500 time step. Okay, so let's wait for convergence. Okay, so the solution is converged after 662 iterations. Now we can check the coefficient of pressure plots in ParaView. So go back to ParaView, and again just reload the Montessori.form files. Wait a bit. Okay, so the result files are loaded. Now from the times drop down, you can select the converged time step. and also in the drop down you can find the respective variables and also the functions that we defined. So I have selected CP, and if I zoom in to see the contour plot for the building, you can see that it's almost similar to the arrangement, or the contour plot is similar to what we have in the reference article. So here the maximum happens here at 0.85, and the lowest level you have 0.7. so you can probe it here. So here you have the value as 0.88, and below you have 0.7. So I think this result is reasonable for the initial simulation. So in the reference article, the domain size is slightly bigger than what I have used. And also, so I decided to simulate with this mesh settings after a bit of mesh sensitivity study. So perhaps going up to a finer mesh can improve the results a bit more. So in the reference article, they have done the simulation with 2 million cells, and I have done it with half the cells. So this error in magnitude may be because of that. But I think this is reasonably close. And I have created a slice of the domain. And if you look at the slice and the velocity plot, you can see the velocity plot here, flow separating at the top edge and then reattaching somewhere here. And also if we see the vector plot, you can see that the vector plot's also resembling with what we saw in the reference article. So you have this recirculation here, and you have the reattachment happening here, and this is the reattachment length. Yeah, so you can validate those things. Then so I think the results are acceptable, and I think this video helps you to try it out and to get started with the cases in OpenFOAM. And I think the workflow and everything will be really useful in whatever simulation type it is. And thank you for watching.